So our next speakers are Sophie Neubauer and Philipp Neubauer. And I will again give you the opportunity to introduce yourselves.
Thank you very much. I want to welcome everybody to our presentation today. I will wait with the introduction a little bit and dive right into our topic, trustworthy autonomy. We're going to talk about neural network controllers in cyber-physical systems. And right away, I want to ask the question, where are the integrations of neural networks in cyber-physical systems? And the second question is, why aren't they so many right now in the real world? Let's have a look. So we collected a few examples of obviously implementations or integrations of neural networks in actually real-life applications. And we see that especially in dynamical environments and safety-critical environments, we have high risks for potential damage of property and harm for people. And what is the reason that we need to overcome so that these integrations are possible? We need guarantees. We need guarantees for proper functionality, and we need guarantees for safe functionality. So my name is Philipp Neubauer. Next to me is Sophie Neubauer. We are the founders of DatenVorsprung GmbH. We're a small company based in Vienna, and we are developing solutions for formal verifications of AI systems for research and industry. We are engaged in several research projects in different domains, such as tourism, so AI control in or tourism flow control via AI technology, embedded technologies in the field of sensors, or in individual mobility. On the other hand, we're working for industry, so we're developing these and providing these solutions for industry partners in the field of robotics, automation, and so on. And during today's talk, we want to dive into formal verification, into the topic of verification of such systems, and have a tech dive into this topic. So what we are dealing with in the so-called AI life cycles, we are now looking at the very end. So the part where it's about testing and formal verification and validation. And in this sector, we developed specific technologies so that we can assess formal guarantees for neural network control cyber-physical systems. And now I will hand over to Sophie.
Thank you. So the main topic is always trustworthiness, how to trust these systems. And what do we mean by trustworthiness is that we do not want the system to reach unsafe states, such that it can harm people or something can break. So something that we don't want to happen, that it happens. And an example is we have a controller who is trained to swing up a pole, and this is just a small example to see what we mean by verifying the systems. So there is a trained controller, then we say, okay, unsafe states are any states with an angle extremer than plus or minus 90 degrees, or if the cart goes outside the rail. And the initial set of states is the downward position, so we wrote it down minus epsilon until epsilon, so with a small movement. And what we want to state is whether the neural network controller will always be able to swing it up and have it in a safe position, because you can always test a lot of different initial traces, but you need some guarantees of what will happen in the states between the ones you tested. And so the safety criteria would be to provide guarantees for not reaching the unsafe states when starting inside an initial interval. So the setup is we have a cyber-physical system which is a physical system which is being controlled by a neural network. There are control variables going to the system, and the system gives back state variables, or their observed variables, and the neural network gets these again as an input. And normally a system like this is trained via reinforcement learning or imitation learning. And then we want to perform reachability analysis of this closed loop system, so the neural network system together with the physics environment, so with nonlinear differential equations. And mathematically, it's undecidable to exactly predict the behavior of the system, so we need to somehow over-approximate this behavior. So the problem is we have nonlinear differential equations with initial conditions, as I stated before, for example, this minus epsilon until epsilon, or it can be also n-dimensional. And we want for every time step t have a bound over all possible states that can be reached at this time step. So if we have here the time axis, then we have our initial set of states. Now let's say with two variables, x and y. We have a nonlinear dynamics describing how the system evolves over time. And what we want is a bound, such that we can be sure that the real system is inside these bounds. And these bounds also help us to check for intersections with unsafe regions. Like here we can say, okay, our bound does not intersect the unsafe region, so also the real system is safe. But another crucial thing is to have a bound that is as tight as possible, because otherwise, like here, we would have a false positive. Our bound here is intersecting the unsafe states, but the real system is not intersecting it. So yeah, we need tight bounds in order to really be able to use the system. Yeah, and we combine the AI system with the nonlinear ODE to make this analysis. So there are two possible ways we try to go, or we can go. One is with formal methods, and the other one with statistical guarantees. So if we see here another plot, so here is x and y, again, two state variables. The z-axis is the time. The black lines are sample trajectories, sample traces, and you see this tube which is bounding the trajectories. The orange one is with the symbolic method, so with the conservative guarantees. It's faster to run, but it blows up over time. As always, I don't know if you know the problem with interval arithmetics, if the errors sum up over time, so you cannot do this for a long time horizon. And with the statistical method, you can be much tighter around the state, so you don't have these false positives. So this is why in this talk we will concentrate on these statistical methods. So we have a tool, it's called GoTube, and it performs this formal statistical verification, and it sees reachability as an optimization problem. So we have again here the initial set of states at time t0, and we want to, so the blue ball is the initial set of states, then here this blue shape is how this initial ball evolves over time, so how it looks like at time tj, and we want to find this ball which bounds it. So what we do is we sample from the initial ball, from the border from initial ball, and we want to find the maximum distance in a time tj such that we can put again a ball around it. Yeah, so this is basically the optimization problem that we're trying to solve. So what is the point, or what is the maximum distance to the center at time tj? After having the sampled points, we call it Lipschitz caps around the already sampled points, and it's to define, okay, in this region we know already what can happen. So we use the Lipschitz constant, which defines somehow relation between the domain and the range of a function, to state how far can we go away from the points we already know, such that we can be sure that also the maximum distance will stay within our defined bounds. So so we have then inside this Lipschitz cap, we can say the probability that the distance of all points inside this cap is smaller than what we have seen before, is greater than some confidence level that we want to set, 1 minus gamma. And it's a little bit similar to using Bayesians of attraction, but it's computationally better or easier to compute because we don't need the Hessians. So it's more scalable when we go to higher dimensions, which we use in neural network systems. Then a little bit more of mathematics is in getting this bound of the Lipschitz constant, which we need in these caps. Here I will just state, we use, let's say, different theorems. One is the generalized extreme value distribution, which is some kind of equivalent to the central limit theorem. So it states that the maximum of some points, it converts always to in some condition, it converts to a specific form of distribution. Like the central limit theorem, you have the Gaussian, and then there is also the theorem from the maximum value. And we want to fit the sample distribution to, so we have in light blue the empirical distribution, it's a step function. Then we try to fit this generalized extreme value distribution in this dark, in this thick blue line. And then we use Dvoretzky-Kiefer-Wolfowitz inequality to find a lower bound of this and to really have statistical method to have guarantees on the Lipschitz constant bound. And then now the last part of the statistical guarantees is then really saying, okay, how much of the initial ball are we now covering with the Lipschitz caps? So for this we use the area of the cap divided by the area of the initial ball which we have, and by just multiplying these different caps that we have, because we are uniformly sampling, we can make the multiplication of all these areas and then say, okay, we stop the optimization algorithm as soon as we get the desired bound that we're looking for. So it's an input parameter gamma, and we say, okay, we want to have at least 1 minus gamma confidence, for example, 95% guarantee or 99%. So it's an iterative algorithm, which we do until we reach this bound. Then in the experimental evaluation of GoTube, we can see when we compare it with with this symbolic method, which is the orange one, we can use it now in a much longer time horizon. As an example for this inverted pendulum, which we had before, this LRTNG and the other symbolic method were able to verify it for 0.1 seconds. So it can just say, okay, in the next 0.1 second, nothing unsafe will happen. So it's a nice theoretical result, but in practice, it cannot be really used. So this is why the statistical approach is much more valuable in the real world, because it can compute these bounds up to an arbitrary time horizon. It also stays really tight around the sample traces, so we avoid these false positives I mentioned in the beginning. And it can also trade runtime for reach chip tightness. So if you want the algorithm to be faster, you can say, okay, let's make the bound a little bit wider and don't enclose it so tight, and then it's faster, the algorithm. So in summary, the main problem we are tackling is trustworthy autonomy in safety critical systems, as Philipp introduced already. With GoTube, we have the statistical algorithm for formal verification of the system, and it's scaling now to long time horizons. And then where are we going? So in industry, in general, there is no accurate model of the plant, because now for GoTube you need really the model of the dynamics. And then if you think of autonomous driving and also how the other cars are behaving, so everything together, you cannot just write down what's happening there. So this is why we're working on the theory and also real world experiments without having the model of a plant. And the goal is to have safe neural network controlled system and to really be able to use the power of neural network also as controllers and still having trustworthiness and reliability when using them. So if any of you have questions, please go on. And also if you have ideas on where this could be used, or if you have maybe use cases where we could do this, we would be happy to discuss this.
As last words, I want to mention, as you see, this is a quite important topic when it comes to applying AI controllers in real world. We are evolving quite fast. Our technology is available publicly, and in any case you are interested in being or in cooperating in test cases, feel free to contact us anytime. Yeah, and now we're open for questions. Thank you very much.
Thanks a lot. Are there any questions from the audience? We would like to start.
Thank you. So, if I got it correctly, I see how this can help me with, let's say, linear regression problems or some, say, more limited problems. But how can it help me with, you had the example of autonomous vehicles, like being sure that I didn't miss any corner cases in my more complex computer vision design. That's not exactly where it is pointed to, or am I mistaken? Maybe I don't see it yet.
Do you want to answer? It depends on the setup, on the problem setup. So for example, if you look at an end-to-end controlled system where vision is a part of it, we for sure can do an analysis of this system, where we can do the calculation of these guarantees for the output of the system. What we need in that case, or for these two technologies, we need the equations of that system or some kind of simulation. So I will give you another example where this is also very important. If you look at the ISO norms for formal verification, so that you can certify some kind of AI controller or application in industry, you need to go through this kind of calculation. So in that case, for example, if you want to certify your simulation, the simulation is the basis for the calculation of the reach tube. In real life, so if you want to check your real life application, as Sophie mentioned, we're working on a system where you can directly interact with the output of the real life implementation, and you get guarantees on this. So I hope I could answer your question, but basically it relies on the setup, how your AI is implemented. And for example, if you have a vision problem and there is some kind of discrete step, classification step, where you classify an image, we have to deal with a little bit of a different approach, because this messes up our guarantees a little bit.
Thank you. Another question.
Thank you. And is your system also ready for changing the environment? Let's say if you're like the cars driving in the highway and there is a change in the weather, is the system ready for that?
Very interesting question, since this is a topic we're actually working on. So it depends on where you want to put the guarantees on. So same question, what is the setup? Do you say that the setup is a different spectrum of environments or of images? And for this spectrum of images, I want to guarantee some kind of functionality of my system. So if we take this whole setup as the box, then this is possible, yeah.
Thank you.
Mm-hmm. It sounds also like a good use case for digital twins, because you would then verify the guarantees on the digital twin and measure it with real-time data coming in, perhaps.
Yeah, for sure.
Mm-hmm. Another question.
I'm interested in the assumptions that you have on your state spaces. So am I correct that this only works with continuous state spaces?
Yes, continuous state spaces and Lipschitz continuous functions.
And that will be the next question, yeah.
Exactly.
Okay,
yeah.
so scenarios where I just have images as input would not work in this case because these are discrete state spaces and yeah, you need continuous ones.
Exactly, but we're working on exactly these images as an input right now also, such that we can modify, that we can also deal with the images as input.
Okay.
Yeah.
And have you had complex state spaces currently where these boundaries that you have, that these guarantees that you put around the dynamics function, are maybe even fractal?
Until now, not. It was always, that you could really bound it like this. But what dynamics?
I don't know. I was just
suggesting?
thinking about like
Yeah.
in reality, in real life, there might be something that is like, especially in the state space, like really. I mean, it always depends on what's safe state and what's not a safe state, and these boundaries might be very intertwined. So I wasn't sure if you maybe have already come along such a scenario, but I could imagine that this is a very tough problem then.
But what we had is, if we start at a big initial ball, that the traces go into different directions, so that it somehow splits up. A few goes to the left, the other ones goes to the right. And then the tube would be around all the traces.
Okay.
And then maybe if there are unsafe states in the middle, and the traces maybe would not reach the unsafe state, because the one would be going left around them and the other one on the right side, but it would be inside the tube. So this we had already.
Okay.
But yeah.
Thank you.
Great, thanks a lot. Any last questions? If not, I'm already secretly walking towards the gifts. I would like to thank our speakers again for this nice final presentations.
Thank you.
One gift for you, one gift for you. And I would like to ask for a final round of applause for our final guest.